All right. Well, welcome, folks. This is the June 2021. It's not 2121 yet, I don't think. A meeting of the Pikes Peak Chapter of the IEEE Computer Society. I'm your host, Gene Freeman. I'm the chair. Tonight we have a brief prehistory of voice over IP with Steve Casner, which should be quite interesting. Couple of housekeeping comments. Please do mute your microphone during the presentation. Usually we also turn off the cameras just to save bandwidth. And I have the ability to control that from my end. So if you have questions, put them into the chat and I'll be collecting that up for after the presentation. This particular presentation came about kind of an interesting way. Both our speakers, Steve Casner and I, both attended Occidental College around the same time, but we were in different tracks. He was in mathematics, I was in the art building, and I also was not on campus much, so we actually didn't know each other, but his wife I had actually known from the high school days. So anyway, we get an alumni, junior high, right. There's an alumni magazine, and you know, comes out every quarter from Occidental. And I opened it up sometime last year, and there's, you know, Karen and Steve, and they're talking about a computer science chair that you endowed, a professorship. And Occidental did not have a computer science department until 2017, from what I read. So I saw that, and I also saw that Steve had won an IEEE award, network award, and or internet award.
Right.
And I thought, wow, you know, here's somebody who went to school at the same time, and IEEE award. Sounds like a speaker. So fortunately, I was able to convince Steve to give this talk tonight, and I think you'll enjoy it. We are recording it, so if you can't catch it, you can see it then. I'll also mention that I think, you know, 2 months ago, Mark Holthouse, who is on tonight, he did a very good webinar on speech recognition, and there's some connections here, so I find that interesting. So with that, I'm going to talk a little about Steve's bio, and then we're going to turn it over to him. So Steve received his BA in math from Occidental College and an MS in computer science from USC. And I'm going to explain some of the acronyms because, you know, anytime you deal with the internet, there's a lot of acronyms. So at the ISI, which many of you may have heard of, the Information Sciences Institute at USC, he implemented protocols and software for some of the earliest experiments with packet voice on the ARPANET beginning in 1974. And then he extended this work to video teleconferencing on higher bandwidth networks in the 1980s. He was chair of the Audio Video Transport Working Group of the IETF. Audio Video Transport's ABT, and the IETF is the Internet Engineering Task Force, which most of you probably know. This is from 1992 to 2003. He was principal editor of the Real-Time Transport Protocol RTP specification from the ABT Working Group. Starting in '92, he was the organizer of MBone, a virtual network which enabled live streaming of IETF meetings, including return audio from remote participants. I mean, today, again, like a lot of these things, we take them for granted, but obviously at one point it was new stuff. It also carried the first internet radio broadcast. So 1995, he took this experience to the commercial arena with packet-based audio and video technology for conferencing and streaming at Percept Software, which was acquired by Cisco in 1998. And you probably know that WebEx, which is our provider tonight, is a Cisco product. Now, whether it has some of the Percept software, Steve could tell us, or at least have some idea. From 2000 to 2014, he worked on network performance measurement and routing analysis at Packet Design. And then Steve and Eve, I don't know, is it Schooler or Schuler?
Schuler.
Schuler shared the IEEE Internet Award in May of 2020. And the citation reads, for distinguished leadership in developing standards for Internet multimedia and formative contributions to the design of Internet multimedia protocols. So really excellent. So I am going to now stop sharing and allow Steve to take over. Steve, whenever you can get the muses to align.
Right.
They're going
Okay.
to give you a hard time because you're one of the inventors, you know.
Right. So you asked about Precept software and WebEx. I think there's no direct relation between those two, but the products we have from Precept software were sold by Cisco for some time. It handled doing IP multicast, like intra-company broadcast, for example. That was the nature of our product at that time. So good evening, everybody. I'm happy to come and give you a talk. I hope that you find it interesting. As you saw, in the introduction, there's a lot of references to protocols, and so I hope that at least some of you are at least a little bit familiar with the notion of developing protocol standards. I do have some pictures of bits in protocols, and that might be boring for some, but I hope that at least it rings a bell for some of you. I chose as my background this evening a view of the building at ISI, Information Sciences Institute in Marina del Rey. It was a very nice place to work. We had the top 2 floors of that building. And one thing I want to point out is the satellite dish on the roof there. I'm going to reference that in a slide quite a ways down through this talk. So let me go ahead and get started with the talk. First couple of pictures, and this first one is for Gene's benefit primarily. This is the IBM 1620 computer at Occidental College. That's Chuck Seekins, Professor Seekins there, helping a student I don't know that was before my time. But this is the first computer that I programmed, and so it's near and dear to my heart. I had worked on a project to build an emulation of this for the Computer History Museum using a real front panel and a Raspberry Pi to make it go. That's just a little side note there. And then a second picture. I am not a member of IEEE, but I want to establish my EE credibility here to say that I did work on this project at Occidental to interface this D17B Minuteman guidance computer to the 1620 so that we could use it for lab data acquisition. Sadly, that project never quite got to completion. Like senior graduation got in the way, but at least it was something that I found particularly interesting. So my background is in mathematics, but I always have considered electronics to be my hobby, my side interest. I am a life member of ACM, even though I'm not a member of IEEE. The ACM seemed like a closer match when I was a student. So anyway, that's enough background. I'll get to the talk. And this talk is adapted from one that I gave jointly with Danny Cohen at Google in 2010. And it's about the work that we did together when Danny was my supervisor. Danny was a life member of IEEE, unfortunately passed away a couple of years ago. For those of you who are also life members of IEEE, Danny complained to me frequently that IEEE required the life members to renew their membership every year, even though they were life members. And he would forget to do that, so his email would stop working. And I had to put a reminder so that I could help him get his email, so that get him to renew so his email would still work. Jean mentioned the problem of acronyms, and so these next couple of slides are loaded with them. But the point of these slides showing a timeline is just to give you a feel for the period of time I'm covering here. It's all quite a ways in the past, from starting the beginning of packet switching to the development of ARPANET. Now, Mark, as Jean mentioned, Mark talked last month about ARPA, which became DARPA, and then ARPA, and then DARPA again. And the work on speech recognition that went on sort of in parallel. Some of the same people were involved in the work that I'm talking about and the speech recognition work. So ARPA created a network that was used by our research groups in both of those areas. And then we took this crazy idea to try to take a network that was made for doing file transfers and remote system access and try to do the crazy idea of putting packet speech over it, real-time speech. So that's what this talk is really mostly about. We were able to actually do conferences, communication over the network starting in 1974 with the continuously variable slope delta modulation encoding, that's CVSD, and LPC is linear predictive coding. So part of the work had to do with creating those encoding methods. We did some voice messaging with voice messages stored on the data computer, which was to be this giant computer of, I think it was a terabyte, which isn't so big anymore. We did multi-site conferencing, and then we were able to transition from the ARPANET with its local protocol to TCP over the internet. And that's the second half of this talk is about that transition and the development of protocols in the TCP IP environment. Jean mentioned the MBONE and the broadcasts we did from IETF meetings. That was starting in the 90s. And the term VoIP doesn't actually come until 1995. So that's why this is a prehistory of VoIP, because most of it's occurring before VoIP actually existed as a thing. The work we did was included by others like ITUT, adopting the real-time transport protocol for their H323 conferencing protocol. And of course, the work was published as a standard in the IETF. So that's sort of roughly the timeline that I'm covering. And Jean advised that I should start. Most of you, or many of you, probably know what packet switching is all about, but Jean advised that I should start with a description that covered it. And so the traditional telephone network was circuit switched, and going way back, initially the switches, the idea of a circuit switch network is that when you make a call, a circuit is established from the source to the destination for data to flow over, and that circuit is there continuously for the voice or data, whatever, to flow over until the end of the call. Initially, The switch was implemented as women sitting at plug boards and patching cables to establish a connection so that there would actually be a pair of copper wires connected all the way from the source to the destination. That was changed to stepper relays that did the switching automatically, and then changed to digital circuits of multiplexed channels where the line from the source phone would still be analog, but the path in the middle was digital. Nevertheless, it was still a circuit that was maintained for the entire duration of the call. That compares to packet switching, where we take the continuous stream of data for voice and chop it up into little pieces with data and a header that tells how the packet should be routed through the network. The switches look at the header and figure out how to send it. And that decision may change from time to time. So you see in this illustration that some of the packets go one way and some go another. And then finally, they're delivered by the address information that's provided in the header. They're delivered to the destination, where the destination may have to put the packets back in order and figure out the timing. So that complexity is what the protocols we were working on was all about. So as we said, this work began over the network. On the first, or one of the first packet switch networks, the ARPANET, which began in 1969, had 4 sites at that time, and the reason for building the ARPANET, ARPA's motivation for building the ARPANET, was that they wanted researchers to be able to share computers, so that in part they didn't have to buy a new computer for each researcher, but also to foster sharing of information, sharing of ideas to enhance the development of the technology. But in addition, the way things had worked is ARPA would have a terminal in the office connected over a leased line to a researcher's network in order for the researcher to be able to demonstrate things to the folks at ARPA. And then they wound up having lots of terminals across their, arrayed around the office. And that was obviously not a scalable solution. So what they wanted to be able to do was to be able to have a network that connected those computers together and allowed them to remotely access those networks. So that was a great idea. They expanded, the network began at 4 nodes, but it expanded over the next couple of decades to quite a number of nodes. At the time of the initial voice calls that I was talking about in 1974, there were about 45 sites on the network. And we talked about USC Information Sciences Institute. That's the node down in the lower left corner there. We worked with several of the other nodes at BBN and SRI arrayed around the network. So I want you to make note that the cross-country lines here are 50 kilobits each. The kids today don't even know what kilobit means. They only talk about megabits and gigabits. But at that time, that was a big deal. Just a couple of notes about the ARPANET. This is an interior view of one of the IMPs. Each of those sites had one or more IMP, which were the nodes of the network. And it was built on a Honeywell 316 computer in a ruggedized package. There were some different packages that came later. So each IMP, the initial addressing of the ARPANET was only 8 bits. There was provision for 64 IMPs, and each IMP could have 4 hosts. Those IMPs were connected together, as I mentioned, by 50 kilobit lines, which AT&T managed to put together with their Bell 303 modems. But compare that 8-bit addressing to the 32 bits that IP version 4 provides. And now we've exhausted that 32-bit address space. So we're in the midst of a transition to IP version 6 with 128 bits of address in order to accommodate the vast growth of the internet that you've all seen. But as I mentioned, in 1973, I proposed this crazy idea to try to put real-time interactive speech over the network that was not initially designed for that purpose. They created this program that I was part of called Network Secure Communication Project, and it was our task to develop that capability. This was something that the carriers really didn't think was going to work at all. It seemed like a crazy idea. They didn't recognize that in fact this would a few decades later be the way that all of the technology was going. So the idea of this project, simply stated, was that this was just a proof of concept to see if this idea would work for real-time communication. But of course, ARPA really had a number of more detailed objectives. They wanted this voice to be good quality. They wanted to make sure that the latency was low enough to make it usable for interactivity, wanted teleconferencing, multimedia, all of these good things. And in order to be able to broaden the accessibility of this network capability, interoperability with the telephone network was also important. And I'll show some more slides about that a bit later. So the network speech compression or network secure communication project, it went by both names, was managed by Bob Kahn at ARPA. And you see that there were quite a few contractors. ISI is one of several. Walt Brannick and Newman, Culler Harrison, MIT. I guess I don't have to spell out MIT. Speech Communications Research Lab, SRI in Northern California, and the University of Utah. And a key difference in this project from many others was that we were all very cooperative, working on different parts of the problem, not competitive, because we really needed this all to work, all the parts to work for the project to succeed. And in order for it to be interesting, we needed to be able to all talk to each other. So it really was, it was great work for me, a project that I really enjoyed. As I mentioned, the program really had two parts. The speech compression was an aspect of it that we needed in order to be able to get voice over these 50 kilobit lines. And the real-time communication part, making the network able to handle sending traffic back and forth in real time interactively, that was the second part. So this program is mostly about the packet communication part, but I will give a couple slides here about the speech compression. I mentioned on the timeline, we had two different voice encoding algorithms. The first was continuously variable slope delta modulation. That's where it sort of drives along the waveform, trying to either going up or down, trying to track what the waveform was by a bit stream. And linear predictive coding, which actually creates a vocal tract model that is either excited by a sequence of pitch pulses for voiced sounds, or by noise, white noise, for unvoiced sounds. That development was a big part of the work for a subset of the contractors. And that got down to 2.4 kilobits per second for sound quality that was okay. I wouldn't say it was great. But that LPC required quite a bit of mathematics, quite a bit of processing. So it required an array processor attached to, we used PDP-11 computers. This one chose an 1134. We had an 1145. And this white box at the top is the Floating Point Systems AP120B array processor that could do parallel arithmetic. That was an amazing 12 megaflops. Now you can get 5 orders of magnitude more than that in the palm of your hand, but at that time, this was a big deal. Okay, so that's it for the compression. On to the protocols. The protocol that was provided with the ARPANET for hosts to communicate was called Network Control Protocol, NCP. And at that time, this was before the invention of TCP or IP or UDP. NCP was the only protocol that we had for speaking over the ARPANET. And its functions were to provide both addressing and flow control and error recovery through retransmission. These are functions that are similar to those of TCP today. So let me show you sort of schematically what that looked like. Various applications would use the NCP, the Network Control Protocol, which was implemented in the operating system, along with an IMP driver that would control the specialized interface device developed for each of the different computer platforms, the PDP-10, the PDP-11, IBM computers. So that each of those would have an interface using the 1822 protocol to talk to the IMP, the big box that I showed you before. NCP was sort of a monolithic protocol. It was the only one we had available. It provided the reliable, error-free, in-order delivery that was what was needed for sending files between hosts or remote access to a host. And this is what all of those services wanted. You wouldn't really want to have data errors. You wouldn't want to lose data. And as I say, this was the only type of service offered. But of course, that's not what we really wanted for real-time traffic, because you can't get the real-time traffic with data integrity. Let me back up a little bit and say FTP here is file transfer protocol for transferring files from one computer to another. You would like the network to give high bandwidth availability, and you definitely want the file to be delivered with integrity, but it's okay if there's some latency getting the file there. It doesn't have to be there right away, typically. In contrast, Telnet, the remote access protocol, you're interacting with the computer, so low latency is important, and it's still important that all of the data goes in both directions with integrity, but you don't need much bandwidth because you're just sending keystrokes back and forth. So for real time, we need both high bandwidth to send our audio streams, and we need low latency for it to be interactive. But what that means is that we have to give up data integrity because we can't achieve all three at once. So for real-time communication, we don't really want to retransmit data. That's the key notion here. for many kinds of real-time data, there will be new data that's coming along continuously, periodically. And so retransmitting the old one doesn't really make sense because that old data may obsolete the new data. Excuse me, the new data may obsolete that old data. So you might as well just send the next one if the previous one got lost. And the last two lines on this slide come from Danny Cohen. The real-time data is like milk. If you don't have enough room to store some older milk and some newer milk, you want to keep the new one. For non-real-time data, it's more like wine. If you don't have enough room in your input buffer to store both an old packet and the new packet, say you miss the old packet, you need to keep room in your buffer for that old one to be retransmitted to you, and maybe discard the new one if you don't have enough room, because you need to get the old one before you can have the new one and deliver both of them to the destination, to the application. So what we needed to do was to bypass the NCP that was trying to give us this reliable transmission and just get raw packets from the raw packet service from the IMP. Now, this is something that the folks who were controlling the ARPANET were really reluctant to do because they were afraid we were going to blast through the network and cause the IMPs to crash. So we had to ask them to, initially at least, we had to ask them to enable us on a time-by-time basis to send these type 3 messages. Oh yeah, so there's the diagram is a little bit wrong. It says type 0 and type 3. Really, they were all type 0, but it was subtype 0 and subtype 3 messages for those who are keen about details. So we developed, to go over this raw packet interface, the network voice protocol. And it has 3 pieces: a data protocol, control protocol, and then some conferencing extensions. The data protocol is really simple, a small header that provides for sequencing and timing information. The control protocol was a token exchange that drove a state machine for connection establishment and negotiation of capabilities. And then we added on some extensions for conferencing that covered floor control, and you'll see that in the slides and the movie that I will show. Along with the movie also shows the extensions we made to allow voting and other things during a conference. I mentioned voice messaging earlier, and the data computer, we included those extensions to our system, so that basically what we would do is open a voice connection from our source, but instead of going to another phone, another terminal, it would go to the data computer to store the message. So this is a page of my first published paper, where we were studying, once we had the raw packet capability, how much data should we put into each packet? That is, you can take the data stream and chop it up into a bunch of small packets or a smaller number of larger packets. And, oops, sorry, if you send large packets, then it takes a long time to gather all of that data into those packets. And so the data at the beginning of the packet is delayed more than the data at the end of the packet. That adds it into your overall round trip delay. That's the packet assembly time, the bottom line of this graph. And if you send packets too fast, over towards the right here, we're sending packets at 20 packets per second instead of 10 packets per second in the middle of the graph, then the network started to be overloaded, and it would take longer for the packets to get through the network. So we reasoned that there would be some sort of optimum value, which we found, at least under this set of conditions, to be about 10 packets per second. Now, another problem that we needed to solve, which might not have been apparent immediately, or might not be apparent to you all listening to this immediately, is that you need to provide synchronization from the transmitter to the receiver, synchronization of the playout. So I am stepping through 3 stages here. The first is, if we go back to that ancient circuit switch network where a copper pair gets actually established from the microphone on one telephone handset to the earpiece on another telephone handset, when you speak into it, that signal is going to pass through the copper network and come out at the other end with exactly the same timing. It may have reduced amplitude, it might have some noise added, but the timing is going to be exactly the same because it's analog, it's just going in, coming out. With the transition to the digital network, then that network needed to be isochronous so that the sampling clock, where we converted from analog to digital, and the playout clock, where the signal went from digital back to analog to be heard, those two needed to be synchronized. And we have a network that provides a signal all the way through from source to destination, where that might conceptually be 2 parallel wires, one carrying data and one carrying the clock. More often it was the data and the clock combined together by some encoding scheme where it allowed you to recover the clock from the combined stream. But there's a way for the data to get sent through and the timing to also be conveyed right through the network. Now, in a packet switch network, we don't have that. The data gets assembled into these packets. Each one is carrying some data and a header to tell it how to be routed through the network and delivered. At the source, this is the schematic symbol for a crystal here. At a source, that sampling is being done by a crystal. It's in the local computer, the local terminal, and that's driving the sampling clock. And then when the packets get to the other end, there's 2 problems. One, that I've tried to convey by showing that the packets are not evenly spaced as they arrive. They may not even be in the same order as they were transmitted. So that's one problem, is knowing exactly when to play those packets. And the other is that they're going to be played using a different crystal local to this computer. There's no clock signal that's carried all the way through the network. Each of the wires connecting a host will have a synchronous line carrying the bits from one node to the next node, but each of those lines is clocked independently, and there's no clock carried all the way through. In our project, there were a couple of strategies that were used to handle the playback. The folks at MIT Lincoln Laboratory did something was reasonable, establishing a playout clock, basically a timeline based on the first packet arrival plus a reconstitution delay that was intended to allow for variability in the delivery time of the packets. Their choice was to then drop the next packets as they arrived onto that timeline. But if the packet arrived late, after the playout had already passed that point in time and the packet was discarded, their technique allowed the silence durations to be accurately reproduced, but it had this downfall that sometimes you'd get stuck in a mode where for an extended period of time, all the packets were getting discarded. They would adjust the reconstitution delay if they saw that packets were getting discarded, but for that talk spurt, you might lose a big chunk of it. At ISI, we took a more laissez-faire approach, and we just said, if we ran out of packets to play, we would just let time slip until we got the next packet, and thereby automatically let the reconstitution delay increase. Now, this would mean that the silence intervals were not accurately reproduced, but we figured that that was not really a critical requirement. If you don't have talk spurts and you don't have the opportunity to make these reconstitution delay adjustments, what happens? If the playout clock crystal is faster, a little bit faster than the sampling clock crystal, you're going to get what we've all seen many times in our recent experience, where you get buffering and a little wheel spinning because you have to wait for some more data to come in. On the other hand, if the playout clock is a little bit slower than the sampling clock, then what happens is the delay in the receiver will build up the buffer, and the receiver will continually build up. Potentially, if it's a really long continuous transmission, exceeding whatever the buffer capacity is for the host. But in any case, you'll lose the notion of live playback. So ideally, what you want is a playback clock that can be adjusted over fine granularity, and then you can use combinations of timestamps representing the source timing and arrival times representing the destination timing as the equivalent of the round trip timestamp and transmit and receive time pairs that that the network time protocol uses, for those of you who are familiar with that, or similar techniques in the IEEE PTP is, I think, the right name of it, for local area networks. So now you might ask, all of this sounds like a lot of trouble. Why go to packet networks and create all this timing trouble? And the answer to that is that what AT&T had to do in order to make the synchronous network work was establish one master clock in Homedale and a very complicated scheme for distributing that clock over the entire network. It turns out that building up all of that infrastructure to maintain and the rest of the equipment to maintain the synchronous network was much more expensive than the links between routers using Ethernet technology and other things that were scaling up to faster rates much quicker. So really, that's why we take the difficulty of, we work with the difficulty of packet switching and make it work for the real-time traffic. So now what I claim to be the highlight of this talk, because it's better than my jabbering, is a movie that we made and actually shot on 16mm film in 1978 that shows a simulated 4-node teleconference using this CBSD continuously variable slope delta modulated in vocoded speech. You'll hear what that sounds like. And I mentioned that this is simulated because for purposes of making a movie, we didn't actually do the whole thing in real time. All of the functions that were there were actually implemented and working. They were split between a couple of systems, one that was local in-house that had more UI, and then the remote one, which worked across the network. they weren't all integrated together, but they, all of these things, we could do all of these things. I point out that there are 4 sites, one of which is a telephone interface. And I'll speak a little more about that in a moment. First, a comment, the CVSD encoder is the blue boxes that you will see in the movie. Okay, so now the STNI is the switch telephone network interface to establish interoperability with the public switch telephone network. Our motivation for implementing this at the time was that we could only have a small number of these packet voice terminals. And so making use of the telephone network as an access network made a lot of sense. It allowed us to broaden the availability of the packet voice system. So the way we did that was by making this interface that hooked up to a telephone line and interpreted the DTMF, the touchtone signaling coming into the STNI, and was able to produce touchtone signaling going out so that we could place calls from the STNI outbound to another phone. And so that way we could have telephones at both ends. I mentioned here that this allowed toll bypass, which is a quaint notion now, but that was a big thing in those days. And it's similar to what we have more recently is Skype and other services. So that's one aspect. One thing I want you to notice is STNI and the telephone interface in the movie. The other thing I want you to notice is that we had floor-controlled data paths. Sorry about my voice. Now in this WebEx and in Zoom, the participants are all able to talk roughly at the same time, and those voice streams get mixed together and played out everywhere. However, with the capabilities we had at that time, the compression capabilities, we only had one decoder at each site, so we couldn't send multiple streams to a site and decode them all and then mix them together in analog. And the linear predictive coding vocal tract model can't handle encoding speech from multiple speakers, because it would have to model multiple vocal tracts together. That didn't work. So really we were limited to listening to one participant at a time. So we used explicit floor control, where the chair could hand off the floor to different speakers. The chair could speak back to the speaker to coordinate the progress of the call, but all the other participants would only be hearing the speaker and not the chair. So you'll see that going on in the movie. And one other thing I'll point out is that you can see a younger me with darker beard and hair sitting at a table behind the Debbie Drew character wearing a fall colors print shirt. I didn't have a speaking role in this movie. So let me go to the movie now and run that.
All of the voices in this film will be heard as they would to a conference participant. They have been digitally processed to reduce the amount of data which is transmitted by a factor of more than 20. It will sound like this.
You are now a conference participant.
Drew, thanks for calling. You're the first participant.
Oh, great. Only Ted and Rick are here, but they're familiar with the project. Oh, it looks like someone's trying to call in.
It looks like it's Parker from Salt Lake City. Let's see what he has to say.
Hello, Randy? I'm anxious to hear what Drew's group has found.
Well, they're on and can hear you. All we need now is Danny. We haven't heard from him. I don't know where he is.
Oh, you know, it's Thursday. I'll bet he's sailing.
Good afternoon, Beverly Hills, Rolls-Royce. You are now connected with the ISI ARPANET digital voice conferencing system.
Here's Danny now.
Randy, sorry I'm late. Are the others still on?
Yes, they're all here and can hear you. In fact, Parker would like to verify your number. Do you have your data with you?
No, I don't have the exact numbers with me. I could talk now in round terms if you'd like.
Danny, Drew seems to be wanting to speak. I'd like to check that with Parker first, and then I will give Drew the floor.
Drew, Randy wants to hear from Parker about what I just said. Then he'll give you the floor. Sorry. Parker, I hope it's finished.
Thanks. Yes, we're just typing it in. You can expect a message from us this afternoon. Drew, you can have the floor.
Randy, I think it's impossible for us to build a program around general numbers. We really need Danny's exact figures before we can continue this. I'd rather talk when he has them. What does anyone else think?
Well, let's take a tally. Can we reconvene this call tomorrow at the same time? Okay, Parker. We really don't need you anyway. Drew, can you have all of your team members on hand at that time? Danny, let's be on time tomorrow. Fine. We can all make it. We should be able to get this finished tomorrow. Now remember, Danny, you have to be on an ARPANET phone so we can secure the conference.
This was a hypothetical conference using features of two real systems developed at the USC Information Sciences Institute.
Okay, are you hearing me okay now?
Yep, and your slides are up, and it looks like people will have that link. So if they want to go view it, you know, when we
Right, right.
post this, that'll work well. So that was good. We heard most of it. It was pretty good, and especially when Mr. Cohen had that look on his face when he was writing on his calendar. I thought maybe he anticipated
That's
we were going
right.
to have technical difficulties. So
That's
go
right.
on. Thank you. Thank you.
Some things you might have noticed. Now, if you could just barely hear the audio, you might not have heard the screeches or the nature of the CVSD sound. But the screeches on Randy's voice in particular were places where the vocoder wasn't accurately tracking the voice signal. If any of you know Danny, you would have recognized that that was not his voice. His accent his Israeli accent was for people to understand that it was decided to use one of my coworkers to dub in Danny's voice. And you might also have noticed that the way this movie was produced avoided the need for lip sync because that was more difficult. Trying to be able to record the audio and synchronize that with the film was outside the bounds of what we could afford to do with this movie. You saw various interface devices, various terminals, computer terminals that we had at that time, and special little boxes that we used as with buttons on them that we used as the interface devices. So that was all about ARPANET, and so the next step is getting to the internet, which is sort of the modern equivalent. The idea was to replace the NCP that I talked about for communicating between the hosts and the ARPANET imps with TCP that added another layer of virtualization with each host implementing or each network implementing a translation from a generalized network addressing layer of TCP to the addressing layer of that specific network. The initial internet was really just the ARPANET as a core and a bunch of local area networks attached onto it. The packet radio network, PRNet, at SRI was in fact the first one to be gatewayed. What we now call a router was called a gateway at that time. And in 1976, the first gateway between the packet radio network and the ARPANET was put into service. This, I guess, rather than saying born, maybe I should say gestation was over the period 76 to 83. But in 1983, there was a decree, a royal decree that NCP should be disabled on the ARPANET, and all hosts thereafter were required to use TCP and step into the modern age. The way that TCP works is applications either using various file transfer remote access applications, or NVP would hand their data off to TCP, which packages it up and sends it off to the router. It was at the time it was conceived, it was a monolithic protocol that handled addressing, integrity, flow control, error handling, all of that together. So this slide may look familiar. TCP provided that order-free, error-free in-order delivery that everybody wants. But you're going to guess what comes next. We didn't really want that for our real-time voice traffic either. And so what we needed to do was split IP and TCP. And that actually happened with the third version of TCP. So a geeky trivia note that you can trick your friends with is that in IPv4, the v4 doesn't refer to the fourth version of IP, it refers to the fourth version of TCP, from which IP was separated. So IP took on the envelope role from the monolithic TCP, that is the addressing, the delivery mechanism, and TCP was the letter inside the IP envelope, handling error control, integrity, and that kind of thing. So what was done at the time of the split was to come up with UDP, which is a very simple protocol, layering on just a little bit of multiplexing on top of the IP layer to be used by real-time applications like our NVP2. So I also mentioned at the beginning IPv6, which is the transition from IPv4. And so you might be wondering, what happened to IPv5? Well, in fact, that was the stream protocol, ST, which went through a couple of generations. This first one was this first document, IEN 119, was written by Jim Forgey. And this is another link to Mark Holthouse's talk from May. Mark showed a slide of papers about various aspects of this speech recognition work, and reference number 18 was authored by Jim Forgey. So the stream protocol in its two iterations was a connection-oriented protocol, not a datagram protocol. So in the sense, that was something more like the telephone network, where there would be a connection setup phase that happens before the data gets to flow. That setup phase allowed establishing per hop identifiers that enabled using a small, more compact header. And it also enabled setting up distribution, not just across one link for point to point, but also point to multi-point. And it allowed reserving network bandwidth for those networks that had a mechanism of dedicating bandwidth to particular traffic. So this was sort of a parallel effort to IP, and there were many detractors who really thought best effort IP was sufficient and the preferred solution. So that's why you don't really see IPv5 at all today. But a primary reason why we had it was that it was needed to work with the satellite network, shared channel satellite network that was our successor to the ARPANET in this packet voice work. The way that the satellite channel worked is that you could either send a datagram, which meant you had to, in a pre-assigned slot, say, I want to send a datagram, and the shared algorithm would come back and say, okay, you can send your datagram in this time slot. Or you could reserve a stream, you could set up a stream, and then you had a pre-assigned time slot that you could send your data in only one hop instead of two hops. And since reducing to one hop was critical for our interactive packet voice, that's what we did. So we needed ST to be able to communicate to the network layer our connection setup and our bandwidth request. And I mentioned at the beginning, the satellite dish on top of ISI, that's what's shown in the red ellipse here. We had quite a range of devices hooked on to this network by 1982, and the sort of wrap-up for the network secure communication program in 1982 showed how much advance we had made from 1973, 1974 timeframe, where we had voice terminals for LPC that were enclosed in a little box of 1.5 cubic feet. We had, in fact, an LPC encoder that was implemented on one digital signal processor chip. So we were able to handle a larger number of participants in the conference because we had more readily available equipment. So at this point, we went into a period that I described as sort of a hibernation, waiting for the network bandwidth to increase sufficiently and waiting for workstations, terminals, to gain an audio capability so that then we had availability of widespread devices that could talk. That time, those of us who had been on the NSC project advanced to doing some other variations, extensions. At ISI, we developed packet video. The networks changed from the satellite wideband network to a terrestrial wideband network with T1 lines, and the DARTnet for experimentation also with T1 lines. So we had more network capacity, and we were actually making the packet audio and video work to the level that groups not associated with our project were actually using it as a teleconferencing service. Over on the Internet Engineering Task Force side, there were further developments for a reservation protocol and various protocols to try to provide quality of service across the IP network. And importantly, Steve Deering developed IP multicast, which allowed us to send data from the IETF meeting in March of 1992 to sites around the network, making use of an IP multicast overlay with overlay routers that could handle the multicast routing, the special multicast routing. So we actually had sites around the world where the audio from the meeting went out, and actually people were able to send audio to the meeting to be played out as well. And that's where the AVT Audio Video Transport Working Group that I chaired began, and the work on RTP began. After that audiocast, we actually created we allowed the overlay network to become a little more permanent, and created the multicast backbone, this M-bone, where that's North America in the middle, Japan and Australia on the left side, Europe, and even Soviet Union on the right side. This went for some time until the 95, 96 timeframe. There were a number of interesting events that happened. We streamed NASA TV, and in the intro, the first internet radio station was mentioned. We did a distributed music performance at the ACM Multimedia 94 conference. There was a Rolling Stones concert that actually was written up in Newsweek in 1994. So there were a number of interesting things happened there, but it was really experimental. So, Gene, at this point, I get to the protocol work. Should I really drop this because we're behind time already?
Unfortunately, I don't have that cool voting thing that you had in the video. How many slides?
Well, so I do have quite a few left. So so let me just say that I wanted to convey by this slide that the sort of transfer of technology from what we had done in the ARPANET days and the VAT program, which was developed by folks at Berkeley as part of the M-bone work, that went through a couple of iterations of development of the real-time transport protocol to get to the one that is, in fact, in use in FaceTime and a number of other applications that are in use as we speak. We brought in the various notions that we developed through the ARPANET work into RTP to provide the services that it does. There's information about the headers that you can look at if you go back to the slides later. The RTP philosophy was one of trying to keep things very simple and fast. that was how we left it in sort of the 95 timeframe. By 2009, there was some backtracking on that, and things got more complicated. But by this time, the rest of the system was more complicated as well. And you know, I set that aside. Those things could be handled. Also, separate. The RTP is about handling the data. There's also a separate path for the control protocols. Our NDP had really just a rudimentary control protocol. RTP includes something for handling the multicast sessions, but not really anything about session initiation. And for that, you really need the session initiation protocol. And SIP is still in use today for voice over IP telephony. To relate things a little more to the current time, I mentioned that RTP was adopted by ITUT for the H.323 conferencing system. SIP is now fairly widely used today, and RTSP real-time streaming protocol was developed as a parallel streaming application. So to note how this is history versus prehistory, the voice over IP name was only created in 1995. There really was quite a bit of work that led to it that went before then. And this is one of Danny's slides, whether this should be called voice over IP or IP under voice, because voice over IP suggests that IP came first and then voice was added to. Really, the voice came first and IP was inserted under it after we figured out how to make the network work. So voice over IP and packet video are major components of what we're doing these days. Their roots go all the way back to what we did in the 1970s on the ARPANET. And with all of these advances in the networking and everything else, the carriers no longer think we're crazy, and this technology is really displacing all of what we had in the telephone network earlier on. So if you are interested in more about the voice coding, this is a good book that covers something about what we did with the packets and our history that I've talked about here, but talks a lot more about the linear predictive coding. And again, I'll put up the URLs here for various places where you can catch this video. And I haven't yet, I guess, sent my PDF of the slides to Gene, but I will do that for distribution from the Pikes Peak website. So that's it.
Yeah, very, very good, Steve. Perhaps, you know, had we understood more about the pieces, you know, we could do a two-parter. But I think for an introduction and giving an overview, I think it's, you know, excellent. And in terms of that particular video you were showing, looks like we can go and view that on the internet. So,
right. It's really disappointing that you know, we did our test and the audio worked fine. So I guess you really need to do test with the real vehicle somehow.
Yeah, but whatever, right? I always find it fascinating. You know, you get the non-technical types who get extremely upset, at least certainly in the early days of all this Zoom technology. But it's always interesting when the real technical people hit issues and you realize, hey, you know, it's the nature of the beast, right? You just can't qualify every piece of software with every other piece of software and hardware.
Right.
Gene,
so you were collecting some questions. Do you have?
Actually, what I was going to do is take advantage of the modern technology and unmute everyone. And if we don't blow up, we'll be able to ask questions. Let's see if that works. Well, at the moment, it doesn't look like it's working, does it?
Gene?
Yeah, you could unmute yourself, actually.
I've done that.
Mr. Brown.
Gene?
Yes,
Yeah,
we
I
can
hear
hear you.
All right. So for your next foray in WebEx using an IEEE WebEx,
Yes,
you and the presenter can log on to the WebEx 20 minutes, half an hour ahead of time.
now
And
that's interesting because I haven't had that luck when with the link that I get from the corporate office. It lets me in 15 minutes ahead. That's
well,
it.
15 minutes is better than none.
that's
Oh
true.
yeah.
And if you've had, difficulties in a simple dry run, then it behooves you to try it again using the
Sure,
corporate WebEx. Okay,
sure.
and 15 minutes should have been enough to
Yeah.
at least figure out what you were going to do.
Always an adventure. Any questions about the presentation, Mr. Brown?
No, but a comment.
Yes.
At our maximum, you had what, 20 people?
Yes.
21?
Mhm.
And there were 40 registered.
Right.
Okay. Just wanted to confirm.
Pretty normal. That's pretty normal for what I've seen. About half. So I don't know if that's been your experience. You got a kind of a different makeup down there, but
Okay, that's it for me. Thanks. And
Thank you.
I got my section XCOM meeting to get to, so
Okay. Thank you for attending.
I'm going to listen in, but that's it.
Yes, go ahead.
I've been doing telecom and stuff in chain retail stores and stuff like that, in addition to software and hardware engineering. And one of the things that I always kind of like, I'm just in awe of everything's a pattern. Everything is like, oh, that's interesting. That's basically 24 digital phone lines, a T1 line. And is there what was the similarity between the old 50 kilobits per second to using multiple DS0 or a digital POP line?
So I think we didn't have DS0s available at that time yet. So this was 1969 when it started. So I mentioned on the slide that they used Bell 303 modems that ganged together 12 voice channels. And I don't know exactly how the voice channels were implemented or ganged, but that was my understanding of how the Bell 303 modem worked.
Oh, okay. So kind of like a precursor T1 in a way.
Yes.
Interesting. I just find it fascinating and stuff like that. I had some ideas too I'd like to talk to you offline at some point if you got some time.
Sure. I think Gene could pass along my email, and that would be the best way to coordinate.
Yeah, I'll do that when I distribute the slides if it's not in the slides.
Yeah, I'm one of the co-chairs for the Consultants Network in San Diego.
Oh, cool.
Too, as well.
Steve,
all right, that's my question.
Okay, thanks, JP. Steve, I had a question. If you looking back, which problem or problems stand out? I mean, you hit some things like with synchronization, but is really key that when you were able to solve that, it made a big stride toward being able to get this technology to work. Is there something in particular that really sticks out in your head?
Well, the key was that we started out trying to use the NCP and again trying to use TCP, but those really didn't work. So recognizing that we needed to change the base level protocol to allow avoiding the retransmission mechanisms. I mean, so maybe you would say, at least in hindsight, that's obvious, but that was the key enabler. That combining with just figuring out how to get all of this. I didn't really talk about how difficult the software implementation was, getting the data to come in from the array processor and packing it up into packets and sending it out. So it took quite a bit of software development to make that go. But you had that same kind of requirement in many projects. I guess the receiver, the transmitter receiver synchronization was probably the next level, next one down to be in terms of difficulty.
Yes. Yeah, that makes sense. Interesting. Are you aware of interesting challenges in other geographies outside the U.S. in implementing this type of thing? Since some of them had obviously different infrastructure.
So the internet infrastructure has become relatively consistent. I would say that the main so the distinction geographically is how much bandwidth you have. In rich countries, you have more bandwidth and less in others, and whether traffic all has to get filtered through some censorship box, which may affect performance somewhere. But at this point, it provides a fairly uniform substrate. I didn't mention it earlier, but the M-bone actually reached McMurdo Station in Antarctica at one point.
Wow. Very good.
I have a question.
Yes.
Hi.
Go ahead,
So
Jonathan.
I've done a lot of development on VoIP over the years at the low level, network protocol level, driver level. I'm wondering when you envision it's really interesting that it basically took a pandemic to force everybody to finally start using all the technology that's like 25 years old. I'm wondering what you think about microphone algorithms. I think they can call it beamforming or whatever, or different names for it. But if you have multiple microphones, then you could pinpoint the speaker. And the biggest problem with any VoIP, or we're experiencing it now, is that when the telecom guys invented the telephone, they put a huge amount of R&D and effort into the handset to get that as close to your mouth as possible. But now in VoIP world, or video conferencing world, everybody's using their laptop microphones and whatever. So you're never going to get good voice quality because the microphone isn't close enough to your mouth, unless you use like some kind of advanced processing, multiple microphones, DSP. So what's your thought on that?
Right. So that is another reflection of how far we have come with processing capabilities, that you can actually just in the capabilities of one node by itself, bring in the signals from multiple microphones and do a massive amount of analysis on it to be able to try to do automated focusing of the beam. Clearly, what we had in those days was just a simple microphone and used handsets or good quality microphones held close to the mouth, because all we could barely handle with our array processor was doing the encoding. But indeed, in the same way that we can now handle mixing of audio from many sites together, that's not a problem at all. And the kind of things that you bring up of doing at each terminal, using multiple microphones and analysis to try to improve the audio quality, to eliminate background noise, and both improving the audio quality on the pickup level and also on the playback level.
And I have one follow-up question. So when I was developing a lot of VoIP stuff, I tended to get very frustrated with telecom companies for obvious reasons I'm sure you can imagine. So I haven't owned.
Your audio stopped there?
Yeah, I was going to say, was that on purpose? We lost your audio. Were you making a point? No, we did lose your audio, Jonathan.
Oh, sorry. Yeah, so I'm just curious if you own a cell phone, because I haven't owned a cell phone since the early 2000s when I was working on a lot of the original VoIP stuff, just because I don't want to have anything to do with the telecom guys, you know. And so
Wow.
I'm VoIP only, and you know,
Wow.
there, I mean, socially, this actually causes kind of a problem because everybody wants to text you or call you, you know, or expects you have a cell phone. But I'm just curious if you have a cell phone or if you've thought of giving it up.
So I do have a cell phone. I was very late to pick one up, though. I was striving to be one of the last people on the planet to get one, mostly because I didn't want to be bothered by it, and because when we were doing this LPC work, I listened to a lot of really crappy vocoded audio, and I didn't want a cell phone because the audio quality over the cell phone is nowhere near what it was with good quality digital. When I had a phone that was digital on my desk, talking to somebody somewhere else with a phone digital on their desk, and it was 64 kilobits in between, we had quite good voice quality. The comparison of that to the cell phone was really disappointing. So that was another reason. But I haven't taken it to the level that you have of not allowing a cell phone at all, or not completely avoiding telephone company terminals.
That's a great comment. I actually have a good friend who did a lot of work with graphics, you know, and CRTs and then, you know, digital screens, and it took him forever to move away from his CRT because he just couldn't think that you could get as good a quality. So he had these, you know, 50-pound things on his desk for a very long time. And cameras too. He really refused to go digital for a long time. But I think the more expertise you have, you do notice these things while the rest of us go, hey, how do you get along without a cell phone? That's great.
And even when you are using a cell phone to call somebody else on another cell phone, it's quite likely that voice over IP is used in between, or at least the technology of carrying those voice channels over IP rather than a synchronous digital circuit.
That's great. Okay, well, I think we've done a good job with the clock. That was really excellent. Appreciate Steve. When you get me your information, I also will tie it together with the link that I get from IEEE for the recording. They have it in the cloud, and I'll put that together. It may take a week. I'm going to be out of town a few days. Not that I couldn't do it remotely, but I'm not sure what I'm going to have with me. I may leave my cell phone at home. I'm now inspired. Yes, go ahead.
Do you have any opportunity to do any editing of the recording? Because we had quite a bit of dead time there.
We did, and I will look into that. At the moment, the way it comes to me is they basically send me a link since it's in the cloud, and it's that. Now, I suspect well, it's going to be pretty big to download, right? I don't know. I don't do much video editing.
Right.
If you have an interest in that, and we can get the link, and you could figure out a way to do it, I can wait to post. If you know, that's kind of up to you. That takes time, and you put plenty of time in here.
So I do. So I have done a little bit of video editing recently, both to do the thank you message for the IEEE Internet Award. I had to prepare a video saying thanks because we couldn't attend the conference was virtual where it was presented. And similarly for the Vintage Computing Festival, I prepared a video talking about our IBM 1620 emulation. So I have done a little bit of that recently. I don't know what format the video would be in.
Well, I'll tell you what. Let's, I can post the slides, and you and I can talk about it. I can send out a message. We can delay certainly posting the video, and if you look at it and decide you want to do something with it, that would be fine. Or if you could tell me how I might do it, like I said, it's nothing I've done much with. So
right, I was wondering whether the service might provide any opportunity to say delete from here to here or something.
Okay, well I'll inquire.
Okay.
Up to now, it's just been from start to pause, which occurs to me that I'm going to stop the recording at this point.